I'm going to go ahead and get started. Today I'm going to be talking about achieving and understanding adversarial robustness. Obviously, the topic of this workshop is on adversarial robustness. And to get started, I just want to acknowledge domain adaptation, which was great that it was just talked about in the last, by the last speaker. And this is where I've spent most of my time thinking and working over the years. Domain adaptation is really this problem statement where you have a lot of data in one setting and you can learn a great supervised model there, but then the world naturally changes over time and your model may fail to recognize under these new changes. Now, obviously, adversarial robustness is very related to this, but with one key difference. Usually when we're talking about adversarial robustness, we assume that there's a malicious actor who can manually perturb the images. And one such version of this that you'll probably hear mentioned in every talk today is that of having small image perturbations, so small meaning low magnitude, but in such a way that they can have a dramatic output effect. So if you were originally able to correctly recognize this as a panda, you could seemingly add some low magnitude noise. Of course, it's chosen in a very, very specific way. But once you add that, you're able to completely change the output of the model. And this is disturbing for a number of reasons. Obviously, if we want to be able to deploy these systems, then we need to be able to have some amount of trust. And once you deploy into the real world, you kind of open yourselves up to, of course, the natural variations that domain adaptation tries to mitigate, but you also open yourself up to having manipulations, especially when you're talking about digital applications. So when you're sharing media online and you don't necessarily know the origin of said media. So I want to start by trying to gain some understanding into how these adversarial perturbations, how is it that you can have a tiny little perturbation and result in a large change in the output space? So to do that, we're going to take an MNIST digit. These are tiny little digits, 28 by 28, and they're just grayscale. We can vectorize it. We can then project it onto a 2D orthonormal basis. It's going to be represented by this point here. And then we can imagine taking a grid sweep around this center image. So because this is a random perturbation, this just accounts to having random perturbations to the image. So one such perturbation may look like this. And then you can place it through the output model. This is a model that was trained on clean images. And what we want to do here is we want to be able to gain some understanding into how, in this random projection space, does our model vary as we make these minor perturbations. So we could do that and we can view our output image like this. And when we have this output image, what we'll notice is that first and foremost, our model is working well. The training data point is correctly classified as a 0. And what we'll also notice is that there's some buffer around this image, at least in this particular projection space. And we can visualize this projection. We can visualize the buffer around it as being the radius by which you can perturb the image without changing the output prediction. So of course, once you go beyond this radius, you're now going to be labeling it as a 2 in this case. And this kind of visualization allows us to gain some insight into how the decision is being made. Now, obviously, there's a lot of different random projections you could make. You could also do a very similar thing using a projection that's based off of a particular attack, in which case that radius may shrink. As we know, when you take a particular attack, like just the simplest FTSM attack, oftentimes you're able to set epsilon really, really low. You're able to take a tiny step and already change the output label and have a successful adversarial attack. But some things to notice about just this model that was trained in a clean way, and now we're looking at a decision cell slice in a random projection. it's really non-smooth. And in general, this radius, this buffer around the training data point is not that large. And maybe that's unclear because you don't have any context to compare against. Well, let's consider some variants of robustness that we could induce here. And one of the standard ways that people add robustness or buffers around their training data points is through regularization. So here's what happens when we use a very standard form of regularization in deep nets, L2 regularization or weight decay. The first thing to notice is that the decision boundaries are now much smoother. In the prior case, we had a lot of jagged edges. Here, we're getting nice, smooth boundaries. And we still have a radius, though, that is relatively small. So in a work that I did last year together with some of my colleagues at FAIR, what we thought about was how can we induce a larger boundary, a larger radius around a particular training data point. And in order to do that, what we want to do is we want to think about what's the quantity that we can use to measure that radius. And so to do that, we use Jacobian regularization. And the way that this works is we start out with a standard supervised learning model. Here we have an initial training data point together with a label. We can train a classifier. And this gives us a particular output score vector. Now, we can ask to compute the input-output Jacobian matrix to be the derivative of this output score vector with respect to the input, meaning the image in this case. And intuitively, if you think about this quantity, all it's saying is how much does the output vector change in response to an input change. So if we're concerned about robustness and not necessarily a particular attack, but just robustness in general, so any random type of minor image perturbations, then what we're asking is, as you change the input in small ways, we want to make sure that the output doesn't have a disproportionately large change. So to do that, we simply add a regularizer. So this is learned together with the cross-entropy loss in order to minimize this Frobenius norm, which is going to, again, minimize the amount that the output can change in response to an input change. And once we do that, we're able to achieve a much larger boundary around a particular training data point. And to see them all side by side, these are all projected in the same, with the same image perturbations evaluated. And you can see how each of these regularizations affects the output decision cell. And in this paper, we also talked about how you can efficiently compute this Jacobian regularizer. So once we do that, we can, of course, evaluate on standard adversarial robustness benchmarks. And the focus of this paper was not necessarily against a particular attack, but of course, we want to evaluate against some of the attacks that people look at in the literature. So on MNIST, we looked at the PGD attack as you varied the number of iterations. And we compared against things like simple vanilla adversarial training, as well as no defense. We're trying to get some understanding as to whether or not there's an attack agnostic defense that might help with adversarial training overall. And we had some results on ImageNet as well. And these results on ImageNet show how the robustness increases in response to a larger weight on this particular regularizer. But one thing to note here is that as you increase the robustness, so as I increase the weight on this regularizer, this lambda JR, we did get higher robustness in response to more PGD iterations, but it was at a cost. So these dots that I've circled here illustrate how much drop in clean performance you had in response to increasing the robustness in this way. And this is not something that's unique to Jacobian regularization. It's something that you'll observe in most adversarial robustness that I've seen, especially in adversarial training and in methods that build upon adversarial training. So what we're thinking about here is that we want to be able to have a model that can be robust against these malicious attacks, but the majority of the time, the model that we deploy is going to be encountering images that haven't been perturbed. And we don't want to take a 10% accuracy reduction just to be able to successfully defend against those adversarial attacks. So what we did, and this is work that's actually going to be presented at this workshop by Yogesh Balaji, who's a student from UMD. And what we did was we tried to think about whether or not there's a way in which we could induce robustness when necessary. So if we think about that decision cell visualization, and we think about the ball, the padding ball that is available around a particular image, what you would notice is if you viewed this for a number of different images, that ball would naturally change. Some images have more margin around their decision boundary than others. And so we thought about how standard adversarial training works. And in standard adversarial training, you start by training a clean model. You then freeze the model and take a backward pass all the way to the image. And that produces a particular sign gradient image. And you add that together with an epsilon factor. And this is something that's manually set inside of these algorithms, but it's usually set to be very, very small so that you're adding small perturbations to the image before you then train yet another model, in this case, in order to recognize these adversarially perturbed images. So now we think about what happens when you have a couple different images. Here I'm showing two examples from the CFAR10 dataset. On the left, there's an image that is easy to manipulate, and on the right, there's an image that's difficult to manipulate. So we have a bird on the left and a deer on the right. Let's start by looking at the bird. What we're showing here is that this bird has a natural boundary width, or radii, of about 1.49. This is all over 255. And what that means is that you only need a tiny, tiny epsilon, a tiny perturbation before you start misclassifying this. And if you actually use an epsilon of 8 or 16, what you'll notice is that the output image is starting to actually look like a deer. So we've made such substantial modifications to this image that now it's kind of unclear what you would expect a learned model to do. And if you expect it to continue to label this image as a bird, even when it, even to us, starts to look like a deer, well, it's natural to start to understand why you would take a hit in terms of your clean performance, because you're creating an impossible learning scenario. Now, in contrast, the image on the right of the deer is very easy to distinguish. And in fact, it takes an epsilon of about 28 before you start to be able to have a successful adversarial attack. Again, what this means is that this image already naturally had a large margin. And so if we're thinking about how can we increase the robustness around this image, we can use a large epsilon. So this gives us the intuition as to how we might induce an instance adaptive adversarial training procedure. And the way that we do that is we take standard adversarial training, which uses a fixed epsilon, and we instead produce an instance-specific epsilon. And this instance-specific epsilon is going to be chosen according to how naturally robust an image is already. So here's some example images. On the left, we have images that were very easy to perturb and took much, much smaller epsilons than are normally used in adversarial training. And on the right, we have example images that took very, very large epsilons in order to train. And in CFAR, a standard epsilon is usually about 8. So what this tells us is that there are differences in terms of the clean images. Some of them are already naturally more robust than others. And maybe if we take the style of approach where we ask for equivalent robustness on every sample, we're going to be naturally hurting clean performance. We might be creating a scenario where we have an impossible learning solution. So to measure that more concretely, what we did is we took the CFAR 10 data set, and the blue dots illustrate performance for training with fixed epsilons, and they're labeled with the epsilon TR there. So we swept across training with a fixed epsilon from 1 to 8, and on the y-axis, we show the natural accuracy or clean accuracy, and on the x-axis, we show adversarial. So ideally, you'd get 100 on both, so you'd be in the upper right corner. But of course, there's a natural trade-off that emerges. And that's exactly what you see with this blue curve that emerges. As you increase the robustness, you get higher adversarial accuracy, you're pushing more to the right, but you're falling down in terms of natural accuracy. And this instance adaptive framework gives us the red triangle and the red star. So we're able to break away from this Pareto curve and improve simultaneously both the natural and the adversarial accuracy. So in the remaining part of the talk, I want to delve a little bit deeper into understanding defenses. So previously, I was showing decision cells that gave us a little bit of understanding into how an attack might be possible. But then right now, there are a lot of different styles of defenses, and they're all exhibiting similar behavior. So in this recent work that's also being presented at this workshop, led by 2 of my students at Georgia Tech, Fulin and Rohit Mitpali, what we sought to understand was, is there any unique behavior that persists across different defenses? And springboarding off of this line of thought of there being different samples that exhibit more or less robustness, is there a way that we can visualize what a defense ends up inducing on particular samples? And to do that, we started thinking about the likelihood under a given model for a particular sample. Now, of course, the problem is that the majority of our models are discriminatively trained, which means that we have access only to this output prediction, which gives us the probability of a particular label given the input. And usually they're trained with some softmax output. But there's a recent line of work that talks about a way in which we can think about our discriminatively trained models as energy-based models. And this is just recent work as of last year. And they did very simple Bayes rules and probabilistic interpretations in order to create a model that gave you an energy-based interpretation. So here we have a standard joint distribution. Joint distribution being over the input and the output. And the marginal log likelihood would be written like this. We could sum over the label and produce a log over a quantity that we know, which is the output logit exponentiated. But then the problem is that we don't know what this normalization factor is. And this is because we didn't train a generative model. We don't necessarily have this quantity modeled, and computing it is known to be very expensive or even intractable. So how can we start to think about visualizing a likelihood of a sample when we can't compute this z of theta? So what we proposed in this work was to think about relative likelihood landscapes. So again, we have the marginal log likelihood quantity written above. But what we really care about when we're thinking about adversarial robustness or robustness in general is how much does the likelihood change in response to perturbations? And that gives us a relative term. So we want to know what is the change in log of P of x. And this is going to be in response to both the clean likelihood and a perturbed likelihood. Now, when we subtract these two quantities, what you may notice is that z of theta is identical between the two and cancels out. And this is because they're computed under the same model without changes. So this gives us the ability to create a visualization where the center point is again going to correspond to the clean likelihood. So in this case, it's going to be that we have no change. And all the points that vary around it are going to be the response to some projection space. Here, it's just written as direction 1 and direction 2. These could be random projections, or they could be adversarially learned projections. But in any case, what you're doing is, again, you're making perturbations in a 2D space, and then you're visualizing how the likelihood changes in response to those perturbations. Now here, we can now visualize these likelihood maps before and after training with various robustness metrics. So on the top left, we have standard training. And what you'll see is that the likelihood of a sample is very high, or relatively high, for the clean sample. But as you make any perturbation, you start to immediately drop off in terms of likelihood. Now, Jacobian regularization shown in the top right, here shown for a minor amount of regularization, which just smooths the landscape and makes some perturbations more likely, but not all. And then with a larger regularization constant of 0.1, we start to get an even smoother, flatter landscape. Adversarial training with different fixed epsilons is shown in the bottom. And again, what you'll notice is as you increase the robustness, this relative likelihood landscape flattens. So what this means is that these two defenses are inducing similar properties on the model, which is that they're making more and more perturbed samples equally likely under the given model to a clean sample. Now we thought about this concept of flatness of the model. If this flatness is corresponding to a few different versions of defenses, is it some property that we can actually use and learn from? So to do that, we created, or actually this is built off of a quantity that was outlined inside that energy-based model paper called the approximate mass score, which tries to give you a sense of how much mass is underneath this curve. And this is a quantity that we can now compute. And so we did just that, and we looked at how the flatness quantity changes at the same time as the adversarial accuracy changes. So on the x-axis, what we're showing is an epsilon in adversarial training on the left, or the lambda factor, meaning the regularization constant, for a Jacobian on the right. But in both cases, you're sweeping from less robust to more robust. And then on the y-axis, we're showing both flatness and adversarial accuracy. And what you'll notice is that as flatness increases, so too does adversarial accuracy. This naturally leads us to ask the question, does flatness imply robustness? So to study that, we have just some preliminary experiments where we actually took this AMS metric and turned it into a regularizer itself and trained models in order to induce this flatness. What we found is that it performed similarly to the Jacobian regularizer. It didn't necessarily outperform in terms of adversarial robustness compared to adversarial training, but again, this is in response to sort of a privileged adversarial training solution because it's trained and evaluated on the same attack. So we still have more experiments to look into to see how these models perform across a whole variety of different attacks. But this gives you a sense of the different likelihood landscapes in response to different defenses, as well as standard training on the left. And these are, instead of using random projections, we're projecting into a particular attack space. So one direction here is the FGSM learned direction, and the other direction is a random or orthonormal direction. So to conclude, this talk focused on two aspects of adversarial robustness. The first is starting to think about how can we produce a class of defenses that are not specific to a particular attack. And to do that, we tried to look at what are the properties of clean models that may lead us to gain some understanding into why attacks may be successful overall. We then talked about how different samples may naturally have different amounts of robustness, and this is important to observe and take into account when we're doing defenses. And then finally, talked about this new visualization technique called relative likelihood landscapes and how it might be able to be used to gain some understanding both into our clean model as well as into our defended models. So with that, I want to take the opportunity to thank all of my great collaborators. Some of them are going to be at this workshop today presenting posters. Yogesh, as well as Rohit and Fu Lin are going to be presenting later today. And I really encourage you to visit their poster sessions, talk